some elementary functions just don't have antiderivatives that are elementary functions themselves. So we can't apply the fundamental theorem of calculus in order to actually get numerical values to complete an integral. So in these cases, we're going to use numerical techniques to approximate the area under the curve. This is referred to as numerical integration. Now, one of these techniques is called the trapezoid technique. Here's the basic idea. So let's just say that I have some curve. If I graph it, it looks something like this. And as we go from A to B here. And I'm looking for the area under the curve. But whatever function created this, I can't find an antiderivative for. It may not actually exist. So what I can do is I can break this up into partitions. And I'm going to do only a couple here for this discussion. And say, all right, I'm going to start here, here. And I'm going to look at this right there. And I know the equation of a trapezoid, find the area of a trapezoid. I just built a trapezoid. I can find that area. I can make another trapezoid, find that area. I can make another trapezoid, find that area. And I can make another trapezoid and find that area. So with this idea, if I can add up all these, the areas of all these individual trapezoids, I could get a decent approximation for the area under the curve. The trapezoid is kind of nice because obviously as I increase n, if I get more and more and more partitions, see, I'm going to have partitions that are short. So this error is going to be minimal. The way I did this example, this is a huge error right here. But if I remove this value of x in, so I get a bunch of partitions, I can get a much better, or reduce that error and get a much better and better and better approximation. So basically the idea is, like I just said, I'm going to partition this function, or the domain really, into n equal, I'm going to use equal subintervals. Then I'm going to form the trapezoids. Now the area for the nth trapezoid is going to be equal to f of xi minus 1 plus f of xi divided by 2 times b minus a over n. Now this b minus a over n, let's think about this for a second. This is b minus a. This is this total distance right there. That's b minus a. Then I'm going to divide it by n, where n equals the number of intervals. Well, that simply amounts to, if I divide b minus a, say, into 1, 2, 3, by 4. Okay, now that I've got the distance, or the base, I guess, for each interval here, the base of each trapezoid, that allows me to go ahead and calculate the area of the nth trapezoid. So the sum of the area, if I add all of these up, I'm going to end up with a b minus a over twice n. Here's my b minus a, and there's my twice n. That's where that comes from right here. Now, my first is going to be f naught, or f of x naught. That's going to be the value of x right here. This is going to be x naught. This would be x1, x2. If there's a bunch of these, all the way out to xn at b. So it's going to be f of x naught plus f of x1. This would be like this first piece. Then the next one, I'm going to repeat f of x1 again, because that was x1 right here, which was the right side of my first trapezoid, is now the left side of my second trapezoid. So that's going to show up there again. And I'm going to get this repeating. So x1 shows up twice. x2 will show up twice. All the way down to f of xn minus 1 will show up twice. F of x naught, the first one, which is at A, and f of xn, which is at B, are the only ones that's only used once. So I can collect all of this and write it as b minus a over twice n times f of x naught plus twice f of x1 twice f of x2 all the way out to twice f of xn minus 1 plus f of xn. Now, this component right here, this b minus a over n, remember b minus a over n is actually equal to delta x. That's the distance right here. This could be thought of as delta x. So I could rewrite this as this whole piece right here as simply delta x over 2. This says the same thing that says. So it's really a matter of preference, how you want to write it. It's different notation to say the exact same thing. This then leads us to the actual trapezoid rule. It says let f be continuous on a to b. We need a continuous function. The trapezoid rule for approximating this integral, we say the integral from a to b of f of x dx is approximately equal to b minus a over 2n times all of that, which, like I just said, I could rewrite this as simply being 1/2 delta x, or obviously delta x over 2. So this is the formula, if you will, that you use when you apply the trapezoid rule.